Okay, this is going to be a proof of Orr's theorem. So Orr's theorem. Now, I must admit that I hadn't heard of this until recently, and so the proof is quite new to me as well. It took me a few times to sort of wrap my head around the logic of it. I'll try and spell it out as simply as I can. It isn't that difficult, really. It just kind of revolves around a few key facts. And once you piece them all together, it's quite sensible, really. But don't be worried if you don't quite get the logic straight away. Okay, I certainly didn't. Okay, so let's write down what the theorem says. So the theorem says if for all non-adjacent, well, let's put it in symbols first, and I'll write it in English in a minute. So if for all in U and V, which are contained in the vertices of a graph, so they're in the vertices of a graph G. So U and V are vertices of a graph G, such that the edge UV is not contained in the edge set of G. So U and V are vertices, but UV is not an edge. And the degree of U plus the degree of V is greater than or equal to n, then the graph is Hamiltonian. Okay, so that's what Orr's theorem says in symbols, and I'll kind of write it again in English and then spell it out with a actual example. So basically in English, this is saying if for all non-adjacent vertices U and V, so if for all non-adjacent vertices U and V with degree of U plus the degree of V greater than or equal to n. So if for all non-adjacent vertices U and V, the degree of U and plus the degree of V is greater than or equal to n, then the graph is Hamiltonian. Then the graph okay, so that's what it says in English. So if for non-adjacent vertices, the degree of U plus degree of V is greater than the degree of U plus degree of V is greater than or equal to n, then the graph is Hamiltonian. Okay, so that's what it is in English. So now I'm going to draw a picture and show you what it says and what it doesn't say. So essentially, let's have a look at a graph. So I'm going to draw a graph here. So I took this graph from Wikipedia, but it kind of does the job. So got all these connections here. So there we go. And up top. Okay, so let's call this U, let's call this V. They're non-adjacent. Oh, hang on. They are adjacent. Let's find one here. There, U and V. So they're definitely non-adjacent. So the degree of U is 1, 2, 3, 4, plus the degree of V, which is 1, 2, 3, 4. Well, that's equal to 8, which is greater than or equal to n, which is the number of vertices, and n is equal to 7 here. 1, 2, 3, 4, 5, 6, 7. So that says there exists, well, it's sufficient condition for a Hamiltonian cycle. Okay. Okay, so let me draw one where the Hamiltonian cycle actually is. So just in case you weren't aware of it, so we'd come on here, up here, up here, up here, down there, along there, and back down there. So clearly we visited all the vertices once and once only, so it's definitely Hamiltonian cycle. There we go. So it's a sufficient condition for a Hamiltonian cycle. That means if this is true, then it is Hamiltonian, okay? However, it's not a necessary condition. So let me just kind of, so I stole that one from Wikipedia. This one is not stolen from there, but it's kind of obvious. 1, 2, 3, 4, 5, 6, and another one. So this is another graph with 7 vertices. And again, I'll have a U and V being non-adjacent vertices, so maybe U there, V there. So here the degree of U plus the degree of V would be 2 plus 2. Well, clearly that's less than 7, that's less than 7. But however, there's definitely a Hamiltonian cycle. Okay, you can see it's just obvious. You go around the outside. Okay, so if you go around the outside, you visit all the edges, all the vertices once only, so it's Hamiltonian. Start and finish at the same place, and every edge is visited once, so it's a cycle. So despite the fact that this condition does not hold, okay, the degree of U plus the degree of V is definitely not greater than or equal to n, it still has the Hamiltonian cycle. So it's not it's sufficient, but it's not necessary. It's a sufficient condition and but not a necessary condition. There are graphs that's not true, and yet they still admit a Hamiltonian cycle. Okay. Right then, well, let's move on to the proof. Now, as I say, I found this proof, I took a good few readings to actually get my head around this. In fact, I actually wrote out the proof myself a couple of times, and then each little piece sort of clicked in place. So that's what I'm going to do now. I'm going to make write down the notes that I kind of made to myself when I was doing the proof, and then piece it all together at the end. It's not that hard. The proof isn't so terrible, but at the same time, it just needs a lot of kind of back work, I think, really. So the first is note 1. Okay, so let's note 1. The first note is that for any complete graph, so a complete graph, let's say Kn, where n is greater than or equal to 3, that they have a Hamiltonian cycle. So they're Hamiltonian. Okay, you simply go around the outside. Simply go around it. Okay, so for any complete graph, it's Hamiltonian. So let's just kind of spell that out. So here's a complete graph. I will be in a second when I draw the edges. So there's a complete graph on 3 vertices. Let me do the same thing for a complete graph on 4 vertices now. 1, 2, 3, 4. So hang on, there we go. Every vertex connects to every other one. So if I say this is A, B, C, A, B, C, D, so the Hamiltonian cycle would be A, B, C, A. Okay, that's really quite straightforward. You could just say, right, let's just go around this way, this way, this way there. I've visited every vertex once, started at and finished the same place, got a Hamiltonian cycle. And now for something a little trickier, though not much, we've got A, B, C, D, A. And so we're going to go up here, along there, along there. So just going around the outside. It's really simple to imagine that, you know, for higher cases, that's always going to be the case. You can always just go around the outside because it's complete. Every vertex is connected to every other vertex. Okay. Right, so note number 2 is that if you add an edge, or adding an edge to a graph, so start with the graph, then you add another edge. Okay, you cannot decrease you cannot decrease, so you cannot or does not decrease the degree of the vertices. Okay, so let me just give you an example of that. So if you add an edge to a graph, it's not going to decrease the vertices degree. So let's start with a simple graph like here. So let's go down here, along there, and up there. So let's say that's our graph. Then the degree of this vertex is 2. The degree of this one is 2. The degree of this one is 3. The degree of that one is 1. Okay, so now I'll do the same graph, but now I'm just going to add one edge. And we'll know that what happens to the degrees. So let's clear the degrees off. Okay. Right, so let's add an edge then. So I'll add that edge there. So what's going to happen? Well, this had a degree of 2 before, but now it's got a degree of 3. So that's actually increased. Okay. That's gone 3. This has stayed the same as 2. This has stayed the same as 3. And this has increased to 2. So this note 2 is just observing the fact that every time you add an edge, it isn't going to decrease the degree. Okay. So more importantly, in terms of what we're kind of getting towards, if for a graph, the degree of u plus the degree of v is greater than or equal to n, so if that's true for some graph, adding edges is still going to be true because the degree of v is not going to decrease and the degree of v is not going to decrease and n is going to stay fixed. So if it's going to be true before, it'll be true after we add edges. Okay, so if it was true before, it's still true. Okay, so that's note 2. Right, so now we need to look onto note 3. So I can find that. Yep. So note 3. Okay, so if adding an edge to a graph, if adding an edge to a graph gives it a Hamiltonian cycle, so if when you add an edge to a graph, it then has a Hamiltonian cycle, then it already contains a Hamiltonian path. Then it already contains a Hamiltonian path. So let's just kind of get a picture on what we're talking about here. So if I've got some sort of graph, dead simple here. So this graph here clearly has a Hamiltonian path. Okay, really very simple. So the Hamiltonian path would be Hamiltonian path. Let's label this A, B, C, D. It's just going to be A, B, C, D. Okay, come along here, come on there, and up to D. So we visited all the vertices once, and we finished in a different place, and we have only traversed the edges once, so it's a path. Okay, not closed path. But now if I copy this graph like so, move it over here, and now I add another edge so that it is now Hamiltonian cycle. So I'm not just adding any old edge, I'm adding an edge, so it's a Hamiltonian cycle. So I'll add up there to there. So now we've got the Hamiltonian cycle. So the Hamiltonian cycle, which would be A, B, C, D, A. So what we're saying is, if it's got this Hamiltonian cycle, okay, adding one more, when we add one more edge to this, it's got now got a cycle. It must have already had a path. Okay, hopefully that's pretty straightforward now. Okay, so note 4, and then we're ready for the proof. Okay, so note 4 was the one that kind of threw me a little bit. It's the picture, or when I looked at the proof, kind of threw me, but let's just have a little look at it now. So note 4. Okay, so suppose a graph has a Hamiltonian path, So suppose it's got a Hamiltonian path. So let's label that V1, V2, V3, up to Vn. So that's the Hamiltonian path. But importantly, no Hamiltonian cycle. So it's got a Hamiltonian path, but it hasn't got a Hamiltonian cycle. Then the degree of U, or in this case V1, because these are V1 and Vn are not connected. So the degree of V1 plus the degree of Vn is going to be less than or equal to n minus 1. So here, just to be clear, V1 and Vn are not adjacent, because this is a Hamiltonian path, not a Hamiltonian cycle. If V1 and Vn were connected, then it would be a Hamiltonian. We could write V1 here, and it would be a Hamiltonian cycle. So V1 and Vn are not adjacent. So there's a Hamiltonian path. That's okay. There is one of those, but there is no Hamiltonian cycle. Okay. So let me give you a for example on that now. So maybe I've got a vertex here, one here, some here, up here, and down here. Okay, so let's label these V1, V2, V3, V4, V5, Vn. Okay. Now I could put breaks in here, dots, but it made more sense to me doing it like this. But obviously you could have gaps in here or gaps here. So let's call that like that. So here's our graph, and I'm going to have another edge here. So the Hamiltonian path is V1, V2, V3, V4, V5, Vn. Okay. So there's the Hamiltonian path. It doesn't have a Hamiltonian cycle. So this is for example. Okay, now then, what I'm going to do now is I'm going to show you, okay, if this is true, if that we've got, then what we've got to observe that, let me draw a red one on here. Okay, so let me draw this edge here. If this is true, then we can't have this edge here that I've drawn in red. Okay, so observe that Vn cannot be adjacent to any vertex So it can't be adjacent to any vertex that V1 is adjacent to. So it can't be any adjacent to any vertex. Let me say that better. It can't be adjacent to any vertex, or the preceding vertex, I should say. Can't be adjacent to the preceding, can't be adjacent to the preceding vertex that V1 is connected to. Okay, so what I'm saying is, if V1 is connected to this vertex, then we can't have this one connected to the one before. Okay, so you might be thinking, why is that? Well, then if it was, then the graph would have a Hamiltonian cycle, and we said it didn't. But we said it didn't. Okay, so if V1 is connected to, say, V4 here, then we're saying Vn cannot be connected to V3. It can't be connected to the adjacent. It can't be adjacent to the preceding vertex that V1 is connected to. Okay? So, and the reason for that, and here's where we can show that it would have this cycle. So the cycle would start at V1. Okay, so then it would come down to V4 in this example. Then it would go up to V5, all the way on to Vn, back down here from Vn to V3. So that's where the preceding part comes in, and then up to V1. So there we've created a Hamiltonian cycle. Explicitly, that would be V1, in this example, V1, V4, V5, Vn, V3, V2, V1, okay? Visits all of the vertices once, there, and once only. It's a cycle. So because we're saying that our graph does not have a Hamiltonian cycle, then we're saying that this edge cannot be connected to the preceding one. So what does that mean now? Okay, it's okay, good saying that. So for every vertex adjacent to V1, so for, in this case V4, so for every vertex adjacent to V4, to V1, sorry, there is one that cannot be, namely the preceding one. There's one that cannot be adjacent to Vn, namely the preceding one. Okay. So what this is really doing is it's restricting the degree of Vn. So this is really kind of, what this is doing is, this is restricting the degree of Vn. Okay, so let me just go through this again, because this took me a few times to wrap my head around, and it's actually not that difficult. What we're saying is, suppose we've got a Hamiltonian path, so there it is, okay. Suppose there's no Hamiltonian cycle, then we'll get to this part in a second. So let's have a look at that. Here's the Hamiltonian path. Now, because it's got a Hamiltonian path and no Hamiltonian cycle, then we're saying that Vn cannot be adjacent to the one before V1 is adjacent to. Okay, so this red one here is not possible. And the reason is because that would create a Hamiltonian cycle. Okay, so Vn cannot be adjacent to the preceding vertex that V1 is connected to. Okay, well, that gives us some limit on the degree of Vn. So for every vertex adjacent to V1, then that's kind of saying there's one that for every vertex adjacent to V1, then we're saying there's one that Vn cannot be adjacent to. Okay, so for example, if V1 was connected to V5, then Vn could not be connected to V4. If V1 is connected to V4, then Vn cannot be connected to V3. And so on, okay? it's important it's the preceding one, so this loop doesn't have any gaps. Okay, if we imagined that we had a vertex here, then this loop wouldn't connect them all, and so it wouldn't be a Hamiltonian cycle. It wouldn't visit that vertex that was in the middle here somewhere. Okay, so what essentially we've done is we've restricted the degree of Vn. Okay, and that's fine. So how's this going to work? Well, second thing to notice really is that the degree of Vn must be less than or equal to the degree of n. The degree of Vn must be less than or equal to n minus 1. Why? Well, because there are n minus 1 connections to n minus 1 other vertexes. Okay, so we're saying that there must be less than or equal to n minus 1. Okay, well, we can also say the degree of Vn is going to be less than or equal to n minus 1, but we can also say take away the degree of V1, because out of all of the ones that would be connected here, we have to limit, because Vn cannot be connected to any one that V1 is connected to. Okay, so if you rearrange this, we've got degree of V1 plus the degree of Vn is going to be less than or equal to n minus 1. Okay, so that's kind of a quite a lot to take in, really. Okay, I'll go over it one more time. Okay, so this has a Hamiltonian path, okay, but no Hamiltonian cycle. What does that mean? Well, it means that Vn cannot be connected to any vertex or the preceding vertex to the one that V1 is connected to, because if it was, then we could create some cycle. Why is that important? Well, that's important because that gives us a restriction for the degree of Vn. We already know that Vn is degree less than or equal to n minus 1 because it just has no Hamiltonian cycle. V1 and Vn are not adjacent, so that's going to knock off one of the degrees that's going to knock off an edge to here. It cannot be connected to V1. Okay, otherwise they would be adjacent. We also know from this that it can't be connected to any vertex or the preceding vertex to one that V1 is connected to, and so it's this value here subtracted all the ones that are connected to V1. For every one of these, there's one that Vn is not connected to. Rearranging that gives this. Okay, so probably need to maybe watch this a few times, I don't know. It certainly took me a few times to get my head around it. Maybe not so for you, but anyway, let's move on with the final part of the proof now. Okay, so the proof. So this is going to be a proof by contradiction. Okay, so I'll write the theorem again. In fact, let's just copy this and bring it down here somewhere. Okay, so if I delete all that, and delete all that. Right, now we've got a kind of worded copy of it here. Okay, so here's our proof by contradiction. So it's a proof by a contradiction. Okay, so assume, for the sake of contradiction, or for the purpose of contradiction. So we're going to assume for this purpose of contradiction that for all vertices u and v that are non-adjacent, so For all non-adjacent vertices U and V, with degree of U plus the degree of V, okay, greater than or equal to n, that the graph is not Hamiltonian. So that's the opposite of what we want to show. That the graph is not Hamiltonian. Okay. Right, so we've got our graph, and we're going to assume that this is true. Okay. So what we're going to do to our graph is we're going to add edges to the graph until adding one more edge means it's Hamiltonian. Okay, so because adding edges preserves the fact that the degree of U plus the degree of V is going to be greater than, so greater than or equal to n. So that fact is preserved. As well as that, this is always possible because the complete graph is Hamiltonian. N greater than or equal to 3. So what I'm saying is this is always possible. You can always add edges until you get to a point where adding one more edge will make it Hamiltonian, because every n greater than 3, n greater than or equal to 3 complete graph has a Hamiltonian cycle. You can just go around the outside. So this is always possible, and adding edges preserves this fact. Okay, if you add edges, it does not decrease the degree of a vertex. In fact, it might increase it. So it could be more true if you want to put it that way. Okay, so here's where the contradiction. But for such a graph, so after doing this thing, for such a graph, so we haven't done anything wrong yet, but for such a graph, we've just showed that if it has a Hamiltonian path, which this one would have, because it's one away from a Hamiltonian cycle, then for such a graph, the degree of U plus the degree of V is less than or equal to n minus 1. Well, it can't be both then, can it? So that contradicts that degree of U plus degree of V greater than or equal to n. Okay? So this was the note 4. So the note 4. Basically, every graph with a Hamiltonian path and no Hamiltonian cycle. So this is which this one would be. So this is every graph with a Hamiltonian path and no Hamiltonian cycle, which is exactly what you'd have if you add edges until the point where one more edge would make it Hamiltonian. And that's always possible because the complete graphs are Hamiltonian. They always have a Hamiltonian cycle. So in conclusion then, we have what we've just wanted to show. Okay, so we conclude. Our conclusion is for all non-adjacent So for all unadjacent vertices U and V, with degree of U plus degree of V greater than or equal to n, then the graph that's sufficient to be Hamiltonian. Is Hamiltonian. So this is a sufficient, get my words out, this is a sufficient but not necessary condition. Sufficient but not necessary. Okay, well that's going to conclude this part. The proof, strictly speaking, isn't going to be part of what we're being assessed on. the teacher guidance that I have essentially phrases this in terms of being able to apply something. Okay, so let me just find out what it actually says. It says, identify graphs as Hamiltonian by using a given result. Okay, so the examiner might give you a result such as Orr's theorem and then expect you to be able to apply it. It's not, the proof is not going to be expected. Okay, proof is not expected. Okay, one of the reasons I went through this proof was because I wanted to kind of get myself a better understanding of the theorem. It didn't seem very obvious to me when I first saw the comment. It kind of was a bit mysterious. I suppose if you've got enough edges, though, it kind of makes sense that you should, you know, it kind of makes sense that you more likely, I don't know if that's the right way of saying it, but the more edges you have in a graph compared to the vertices, the more it seems as though you would have a Hamiltonian cycle. And I guess this is putting some sort of bound on that, okay? So hopefully that makes sense. I'm going to end the video here. This is not going to be on your exam, just might prove interesting, hopefully.